One of the most common examples of constant acceleration is what we call free fall. Any object that is allowed to fall towards the Earth will accelerate towards the Earth due to Earth's gravity. Any object that is falling towards the Earth is accelerating at a rate of 9.8 meters per second squared. Keep in mind our acceleration direction depends on our coordinate system. If we define up as positive, as we typically do, an object falling towards the Earth has a negative g value. Now we say this, but in reality there are small variations depending on where you are on Earth. However, these are so small that you need extremely sensitive equipment to detect them, and so in the majority of calculations, especially for ours, it is not necessary to account for that. When we say any object, we mean just that, any object. Of course, like many people, your own observations may be trying to convince you otherwise. For example, if you take a hammer and a feather and you drop them from the same height at the same time, you'll probably notice that the hammer will hit the ground first. If both objects are supposed to be accelerating at the same rate, how can one get there first? The logical conclusion seems to be that the hammer is heavier, so it will fall faster towards the Earth. Well, one thing we have to take into consideration is that when we drop something on Earth, it has to travel through the air. Air molecules act to resist the motion of the objects moving through it. We call this air resistance, and it affects some objects more than others. If we were to drop the hammer and the feather in a vacuum, there would be no air resistance, so both objects would reach the ground at the same time. This is actually one of the experiments that the Apollo 15 astronauts did when they landed on the moon. Say you throw a ball straight up in the air so that it has an initial velocity of 13 meters per second. Gravity will immediately begin accelerating it back down to the Earth at a rate of negative 9.8 meters per second squared. After 1 second, the ball will have slowed by a magnitude of 9.8 meters per second. Since it started at 13 meters per second, then its new velocity after 1 second must be 3.2 meters per second. Recall the three kinematic equations that have to do with acceleration. Since an object in free fall is accelerating, we can use those to mathematically describe its motion. We can, however, change them into something a little more specific to our situation. Since an object that falls towards the Earth is accelerated at a constant rate, we can substitute in acceleration due to gravity for a in these equations. So wherever we find acceleration in our equations, we can substitute g. Also, while we would normally record position in terms of x, we are now talking about motion in the vertical direction. When this is the case, we give it the designation of y to distinguish it from horizontal motion. The equations are the same ones, just a little more specific to an object accelerating in the vertical direction. Going back to our ball, we can see how these values can be substituted into the equation for velocity. We know our initial velocity, our acceleration, and our time, so we can plug in all of our knowns to find a final velocity of a positive 3.2 meters per second. Notice that the ball is slowing down, but the velocity is still positive since it is still moving in the up direction. Remember, when the acceleration is in the opposite direction of the motion, the ball will slow down. Now, what would happen if we threw the ball in a downward direction with a velocity of 13 meters per second? Now our initial velocity is in the negative direction. Our acceleration is still negative 9.8 meters per second squared, and our time is still 1 second. But when we put those numbers into our equation, we find a final velocity of negative 23 meters per second. Notice here that the magnitude of the velocity is increasing, but in the negative direction. Here, the acceleration is in the same direction as the motion, so the ball is speeding up. We might also like to know where the ball is at a certain point in time. We can use our equation for final position and plug in the numbers to give us a position of the ball after 1 second. Again, our ball is moving in the positive direction, so our change in position will be positive. In this case, our ball ends up 8.1 meters above the ground. So an object in free fall, regardless of its mass, is accelerated towards the Earth at the same rate. This acceleration rate is known as g, and it is negative 9.8 meters per second squared. We can use this value for acceleration in any of our kinematics equations that we already have.